What I'm going to try to do in this talk is talk a little bit about solutions to time-varying optimization problems, or a particular class of time-varying optimization problems. And really, we're going to be interested in how the solutions to these programs change as variables are added. We'll talk about the framework carefully in a second. And then how we can use these observations to come up with fast streaming algorithms, if you will. So given the very two esteemed names involved with this seminar, Wiener and Fourier, I think Wiener would find a lot interesting in this talk, and maybe Fourier not so much, but we will see a local cosine basis at one point. Okay, so before I do anything, let me just mention this is most of this is kind of the vision of one of my ex-PhD students, Tomer Hamann. So what I'll talk about today made up a part of his thesis. He defended his PhD in January, and now he's at a robotics startup in Israel, actually applying a lot of the things that he came up with during his PhD, and also Joseph Driscoll, who's currently a graduate student at Georgia Tech. Okay, so here is the main thing we'll be concerned with this talk. So we're going to talk about optimization programs, and they're sort of described by a graph. So sometimes when you see a talk on optimization, you see an optimization program stated, and you see a graph like this, some kind of decentralized algorithm where you're trying to minimize the sum of functions, all with a common decision variable, and they're trying to communicate to agree with the decision variable is. That's not what we're doing here. So for us, the graph represents something else. So what we're going to do is say, okay, if I have a graph, with each sort of node in the graph, I'm going to associate a function and a set of variables. So node 1 here is x1 and function f1. And then the connections in the graph, what those indicate are functions that share variables with one another, right? So if we see here on the right here, so f1 depends on x1, x2, and x3. So node 1 is connected to nodes 2 and 3. F2 depends on x1, x2, x3, x4. So it's connected to all three of those nodes. F4 just depends on x4 and x2, so it's just connected to x2. Right, so that's kind of the way we organize these things. We'll talk a lot about how these things arise in different applications. And so then what our object of study here is this optimization program, where basically what we want to minimize the sum of functions. So all this notation means is the variables that go input into FI are all the neighbors of the X variables for all the neighbors of node I. Okay, so that's our object of study object of our study. But particularly what we're going to be sort of talking about, or what we want to get a handle on, is how the solution to these types of programs, how it evolves as this graph changes. Right. So in other words, on the left here, I have this 5-node graph. I solve this optimization program, I have some solution, and then I add this red node over here, which makes this one connection. So the solution changes, right? So the solution, the variables at all the nodes, they'll change, some a lot, some a little. But every time I add a new node to this graph, the solution changes, and I add again, the solution changes again. Right, and so then, what we want to get a handle on is, okay, how does this solution change? And in particular, are there locality properties, right? So just I kind of expect in the applications where these types of things arise, that the solution will change more at the nodes in the immediate vicinity of the node that I added than it will far away. So really getting a handle on formalizing that and what structural properties of these make you say that with confidence. That's what we're going to try to do. And then another way to think about that is okay, if I add this red node, do I really need to update the solution at every variable in the graph? Because if I don't, and this graph is huge, maybe that gives me some real computational savings. Okay, so here, just to set another idea. So here's a poor man's video I made, just a sequence of PNGs I put together. So here, what I have is I kind of have the output of a robot localization problem. So there's some autonomous vehicle navigating in a hallway. And it collects a bunch of data, so it has odometry data. It can see how far it moved. It views landmarks that it can correlate with other measurement times that it's at. And then then it tries to figure out where it was during the entire time, over its entire trajectory. Right, and so you can think of, okay, if I send the robot out and it goes around and collects all the data and then tries to backfit where it was, maybe I get what's in the red, right? So that's kind of like the batch estimate. But really, when I want to solve this problem, I want to do it online, right? So the blue is like the solution of all the data on the graph of all the data that I've seen so far. So as he moves along, he makes connections because he connects to other things where he's been passed. So this solution updates a little bit, right? And what we're trying to really get at here is how quickly these blue dots go to the red dots in some way. Okay, so we'll talk more about applications like this in a little bit. But for now, we're going to look at sort of a very, not simplified, but a very special case of this instantiation. And it's actually a special case that's going to tell us a lot about the general problem. Okay, and that's the problem when, or the case when this graph is just a chain, right? And so, okay, so here's the sort of the form of the optimization programs we want to solve. So again, I have a sum of functions. And the idea is that these functions are being presented to you one at a time. So at time capital T, I get this function f cap T, right? And then also what's introduced is a new set of optimization variables, x sub cap T, and then I add this function to the sum. Right now, the function doesn't just depend on xt; it also depends on the variables from the previous frame, if you will, xt minus 1, right? And so that means that adding this function in, it's not just going to give me a new value for xt, but it's going to correct xt minus 1. And since the xt minus 1 are linked to xt minus 2 through ft minus 1, those are also going to update and so on back down the chain. Right, and so the general idea here is, there's kind of a natural aspect of time here, where at time cap T, I get a function, maybe initialize these new variables, then I solve this new optimization. And like I've said before, kind of our key questions of interest is, the first fundamental question is this problem even well posed, or what makes this problem well posed? And this is what I mean by that. So, what we're going to say is, since the kind of variables that I have in frame little t, those change every time I add a new function. So in kind of the standard notation in fields like this, is I say, okay, the solution after I've seen capital T functions in frame little t, obviously for little t less than or equal to t, this is my estimate. This is the solution to the optimization program at that point. So then the natural question is, as I add more and more functions to the right, as I add more and more functions to the sum, does this estimate settle down, right? So as my guy is moving along, do I finally settle on what was an estimate for my position in the last example? And if so, like, what structural properties of the FT allow this? And if it does happen, how quickly does it happen? Right? And again, what that's going to allow us to do is say, okay, if I'm at, sort of frame 5 here, and now we've seen functions at frame 10, 11, 12, 13, maybe I'm not moving very much. And so maybe you can forget about updating me. And all of a sudden, my optimization problem doesn't keep growing at every time. It becomes something more like a fixed size. Okay, so those are the ideas we're going to try to put together specifically in this case. All right, so there's a very interesting, even special case of this special case, and it turns into something very classical, but something we can add a little bit to in terms of the analysis. And this is be a streaming least squares problem, right? So just as before, like at every iteration T, you get a matrix AT, you get another matrix BT, and you get these observations YT. And the idea is, their model for this situation is that these observations YT, they can be at least approximately written as some linear combinations of your variables in frame T and some linear combination of your variables in frame T minus 1. Right, so this is, again, obviously just a special case, but least squares. There are two, I'll mention two very important problem areas this is involved in. One is the Kalman filter. So, I guess Kalman filter, I think by people like me, is kind of viewed as one of the most important sort of developments in applied mathematics in the 20th century. I remember when I took a class in applied linear algebra when I was a sophomore in college, the instructor described it as the type of technology we wouldn't be able to fly airplanes without. I don't know if that's true or not, but it's important, and it's important in these types of problems. Okay, so here's the idea. It's you have something like, again, if we use our sort of robot example before, you have a state, say it's a position and orientation. It's evolving through some dynamics. There is some uncertainty involved in this dynamics given by this dt. And at every time step, you also make a possibly indirect and noisy observation of the state. So this, what this observation, how we model this observation is it gets sucked through this matrix phi t. And yeah, maybe phi t is underdetermined, maybe it's overdetermined. We're just kind of putting that aside for a second. But what we get to do is observe some number of linear combinations of the current state. Okay, so this is true. I get these observations, and I know these matrices have multiple time steps, and obviously the states are related to each other through these multiple time steps. So one way you can tie all of this information together to get kind of a coherent estimate of the entire state trajectory is to solve the linear least squares problem. So kind of the system you're solving looks like this. So if you want to connect it to and what you're asking for is, whatever my state estimates are, I want them to agree with my measurements, at least approximately at every time step. And I also want them to agree with the dynamics. That's the thing on the right down here, at least approximately at every time step. And so, if you want to connect this to the A and the B we had on the previous frame. So if I suck out one of these 4x4 matrices here. I don't have the precision with my cursor, maybe I won't, but maybe this A2 is like I over phi 2, and B2 is like minus F1 over 0. Okay, so the point is the classical Kalman filter falls into this framework. And this is the type of thing there's been a lot of ink spilled over about how it behaves and how well it can estimate trajectory. Okay, so we'll get to a little bit about what those are, but here's another example of just streaming least squares. And this is an example I've actually used to do something real in application with it. And it's the idea of dynamic reconstruction of a signal from non-uniform samples. So there's lots of acquisition scenarios where you have kind of a continuous signal going by you, and you're able to sample that signal, but not necessarily at equispace points. Right. And the idea is the signal doesn't really start or stop. It's just going on for forever. And what you want to do is get some kind of real-time estimation of what this signal is. So you're collecting, what the idea is here, you collect either one sample at a time or a small batch of samples at a time. You get some kind of estimate about what's going on locally, and then you continue. And an easy way to set that up is you say, okay, if I really want to put this in the language of this least squares, this streaming least squares problem I had on the last page, I can say, okay, let me take my signal and let me window it out. This is sort of just a common trick in signal processing. So I look at the signal in frames. So these are overlapping frames here. And then inside the frame, I represent the signal using some kind of local basis. So here's our local cosine basis on the right here. Right, and the idea is when I get these samples, so that now I'm just drawing, mocking up a set of sample locations, non-uniform sample locations on the x-axis here, right? And these sample locations, like these ones that lie in between these in the middle of these two frames, they involve the expansion coefficients, right? So now I'm capturing the signal with expansion coefficients. So they involve the expansion coefficients from both of these frames, and the samples, over here, they only involve from this one. But nevertheless, if I were to write a sample of this signal, right, it's some linear combination of the samples of the basis functions from the last frame that I want to weight with these basis coefficients, and the sample coefficient from this one, right? And so now we will have the stream problem. We want to cover the x from these streaming samples. So this is nice because it's something we want to do often, and it fits right into this least squares frame. Okay. So again, you can collect this sum up here into this YT is BT, AT, where YT is this collection of samples that you get, say, in a batch like this. Okay, so this is a way to think about online signal reconstruction using streaming least squares. Okay, another thing, that's handy in communications, comes all the time. You have a communication signal. It's sort of going on forever. It's being convolved with something finite, right? It's bouncing off buildings or something like that. And you want to undo this convolution. So the convolution is sort of spread out in time. And so when you see what am I observing when it's at the shift, again, it's some linear combination of the expansion coefficients in this left frame, expansion coefficients right frame. So to just say it's these problems go multiple places in signal processing applications. Okay, good. What the main piece of structure we have, or if you're thinking about this again in terms of a linear inverse problem, you have this kind of lower triangular or band 2 lower triangular system that you're trying to solve in this least square sense. right? And again, as I'm progressing, I'm adding both rows and columns to this matrix on the left here, adding decision variables and also adding observations. And then the key thing is, okay, if I want to solve a least squares problem, I really need to look at like phi transpose phi. And there it's easy to see that phi transpose phi is it's tridiagonal, or in this case, tri-block diagonal. So it has these blocks down the middle, and I can I did what these equations are is basically just how do I write those blocks in terms of the matrices that the problem was posed in. Okay, so that's good. That sort of cues you in on how you might approach a streaming least squares problem. Tridiagonal matrices or block tridiagonal matrices, they're highly structured. There's first of all, they're sparse. And they have this banded structure. Their solutions, their inverses aren't sparse, but their inverses have enough structure that it's easy to write down and sort of an online algorithm for computing the inverse on the fly. And again, the way you think about this, and again, this is all sort of one of the ways people interpret the Kalman filter, is you can think of, okay, really, if I'm sort of have these matrices that's growing. So again, I'm adding these kind of blocks of 4 down this diagonal at every time iteration. I can think of running a running LU factorization. And the idea is that, okay, these Q and these U, they can be computed in terms of the matrices on the previous slide in a recursive manner, right? So in other words, I can run forward keeping a tally of what these U matrices need to be, and they're written in terms and what these Q matrices need to be. So what's along the diagonal here. So there's a recursive algorithm for doing this, and then I can keep track of this kind of intermediate variable. And the way you can interpret this is what I'm doing is I'm running forward and I'm solving, like I'm taking this matrix on the left here and I'm applying it to the G on the right. So I'm doing the L, the L minus 1 times the G on the right. So that's done, and this can be done in just a blockwise fashion. So very quick blockwise fashion. And then once you get to the end, and you say, okay, I've done that. If I have the estimate for T frames in hand, and I introduce a new loss function at frame T+1. So I introduce a new matrix and new measurements. Then what I can do is I can update this intermediary. I can get an immediate estimate for what the optimal state is in this frame. And then I can backtrack going backwards, right? So you can, again, think of this as a very efficient system solve that, not only is a computation efficient, I go forward sweep. And then when I get a new thing, I can backward sweep. So every time I get a new observation, I just do a backward sweep. And that also very much like conforms to our sense of time, right? So again, this is just this idea of tridiagonal factorization. You can see this, almost exactly these equations in any sort of book on matrix computations. And it's also, again, one way to sort of understand how the Kalman filter works. Point is here, it applies to any kind of like streaming least squares problem. Okay, but there's more you can actually say about this, right? And this is where we have to do a little bit of original work. So we can ask, like, okay, when are these estimates like stable? So when do they converge and when do they settle down? And what we can see is like these DT here. So this is what was along the block diagonal of our block diagonal matrix. And this is what was on the off diagonal. The speed at which things settle down and our estimates converge, it really depends on the conditioning of these systems, right? And I guess the general idea is if that, these matrices along the block diagonal of the system that you're solving, if these are well conditioned, just saying like the things are normalized, so the eigenvalues are, within a factor or 2 of each other, and these off diagonal terms are small, right? Then you can basically say that these QT matrices that I get, these are going to be well conditioned as well. Okay, so then the consequence of that is, okay, so again, like what I need for this to happen is this idea of like block diagonal dominance, right? So what it says is kind of these matrices on the off diagonal, they're smaller than these matrices on the diagonal. And I'm also saying these things on the diagonal, they have to be, stably invertible in some sense too. Okay, so if I have that, I can actually say something very nice, right? So I can say, first thing I can say is like, okay, as T gets bigger in this sum, right? So I'm like looking at my solution in frame 5, now I have frame 6, 7, 8, 9, 10. I keep updating what's in frame 5. I can say that this converges to something. So there's some limit in frame t, and this will be true for all t. And not only that, the convergence will be linear, right? So if I say like, if I'm looking at what is how far am I away from convergence at, in frame 5 after I've observed frame 10, well, that's some number less than 1, this delta star over 1 minus delta star to the 5th power, 10 minus 5th power, right? So that tells you something weird. That's right. So it says, okay, the structural property that I need for this kind of streaming least squares problem to make sense are for these matrices, this tridiagonal system that it induces to be block diagonally dominant. And when that's true, I get very fast convergence, and we'll see what that means practically in a second. And again, this is classical, so I put it in quotes here. There's a very simple forward-backward sweep to compute the solution, right? So you have fast algorithm, you have a guarantee of converge, and you have a guarantee of convergence in that convergence equation. Okay, good. So let's just look at like one example. So here's one just stylized example of where like non-uniform samples may be presented to you. So something called like a level crossing ADC, a level crossing analog to digital converter, right? So a standard sampler or a standard analog to digital converter, what it does is at a predetermined set of times, it gives you the signal value, right? So 1 nanosecond gives you 1 signal value, 2 nanoseconds, another signal, 3 nanoseconds, another signal value, et cetera. It's, for certain architectural reasons, it is sometimes much cheaper, or sometimes you can build these things at much higher frequency if you do things a different way. So what you say is instead of returning to you the value of the signal at preset times, what I do is I return to you the times that the signal crosses some preset values, right? And so, these levels have these horizontal covered lines here. So as the signal goes, it crosses this yellow level. So it outputs the sample value at that point. We know what the sample value is wherever this yellow thing is. At the, then across the purple line, and output that time as well too. So at each of these level crossings, I'm outdating the time TM as long as the level that I crossed YM. And you can see the samples are non-uniform because like when this thing is when it's changing more quickly, like it is in this region here, you'll tend to get samples more quickly. And near its peaks where it's changing slowly, there'll tend to be a longer gap between the samples, et cetera. Okay, so that's great. That might be sort of cheaper for you to produce. But when it comes time to do things with samples, people like them to be uniformly spaced. And so, part of, we set up the streaming least squares problem, we can reconstruct a representation of the signal, which you can easily turn into a space of linear, a set of linear space samples by solving the online least squares problem before. And then we can get an idea of like, okay, what do these dynamics really look like? Like how quickly do these estimates converge? So here's just a stylized signal I created. And I said, okay, I've observed a bunch of samples in this region, estimated this signal, I get this. Of course, I don't know anything about what happens in the future. I have in the very recent past, maybe I only have a little bit of idea, but sort of locked on to what's happened far in the past. I make another batch of samples. Again, I can see the red line almost exactly overlays the blue line here, and so on. So you see, like, in theory, when I added these samples, everything in this beginning part, it got updated, but it's only by a very, very small amount. In fact, you can see that in this chart here where I say, okay, look, if I look in frame 4, so this row, this is a log 10. So it's basically telling me how many digits of accuracy I have. So after 2 updates, I'm already almost within 1/1000, 3 digits. Within 3 updates, I'm already within 10 to the minus 5, right? And with 10 updates, I'm like 10 to the minus 13. We can see that's kind of true in all the frames. If I look at the diagonal here of, about 3 down, it's -5. Here it's about -7 something, et cetera. So really for things like this, you can really just update 3 frames in the past and it's still very accurate, right? So that's kind of the practical implication of what this geometric convergence that I get in terms of the streaming least squares problem is. Okay. So just I'll close in saying like for this particular problem of reconstruction from non-uniform samples, I guess what we needed is we need that these system matrices were block diagonally dominant. You can apply what at this point in time are pretty standard concentration inequalities and say, okay, if I take m samples per frame, and I'm trying to reconstruct n basis functions per frame bundle, and I space those samples just happen at random locations, everything will work out. I'll get block diagonal dominance when n is just larger than n, so within a logarithmic factor of n. So again, this is just an application of standard sums of independent random variables to the particular setting that we're interested in. Okay, so that's really just to give you a feel that there are situations in which you can get this. I can guarantee you that you have this property unique for fast convergence. Okay, that's good. So that's basically the story for the least squares case. What we're, so now we're going to build up slowly. So now we know what we have is we have a streaming least square. So we have least squares on this chain graph. Now what we're going to be interested in is generalizing to basically convex functions for on this chain graph. Okay, so just as before, we have a sum of functions. FT depends on both the variables in its current frame xt and the and the variables in the frame before. And what we're going to say here, and what's going to make our lives a little bit easier, is we're going to say the FT are smooth and strongly convex, right? So it's kind of like, it's a recurring theme when you're analyzing the solutions to optimization programs that, if you have smooth and strongly convex assumptions, then it tends to be really related to what happens in the least square set. And then we're also going to see that what happens here. So smooth and strongly convex is much, it covers a really broad class of optimization problems you might be interested in, but they behave in some sense a lot like least squares problems, in that you have this very well conditioning of the Hessians of these types of the functionals that you're trying to minimize. Okay, so we'll see a little bit out here. There's some key structure that carries over from the least squares case, which is kind of why I talked about it for the length of time that I did. Okay. Okay, so again, we're interested in the same type of questions. So what are the structural properties of the FT beside them being smooth and strongly convex? And actually, we'll see that's almost enough for these estimates to converge as t goes to infinity. And how quickly does that happen? So do I get the same linear convergence that I had in the least squares? Now, there's one critical difference here. And that's like when I get I had this nice computational algorithm in the least square sense where I got a new function. I could update all the solutions in the past just by doing this what's called a smoothing operation, going back and just updating all the variables once. And that just happened to come from the particular structure of the least squares problem that I can interpret it as the solution to really solving this tridiagonal system of equations. I don't have that in the general case. When it's in general more complicated, I will. So when I add a new thing, I will have to update all the solutions in the past, at least in theory. It's not just handled with a nice backward sweep, but we'll see in a second that, or in a few slides, that there is you still have enough structure that suggests a very nice outcome. Okay, but first we really want to get a handle on these kind of more fundamental questions, like is this thing even well posed as t gets large? Okay, so here there are two key pieces of structure that we can explore. And they're trivial, but once you understand where to apply them, you kind of see how everything works. Okay, so the first is each of these. Okay, so each of these functions obviously depends on two variables, but there's something else. So each of the two variables only appears in two different functions. So xt is an argument to ft. It's also an argument to ft plus 1, right? And xt minus 1 is argument to ft. It's also an argument to ft minus 1. Okay, and so what that means is, it means if I look at the gradient of this function here, so I look at the gradient of what this sum is here, if I ask, what's the rate of change with respect to the variables in frame 1, only two of the functions are involved in, right? F1 and F2. So in xt, if I look in frame t and I look at the gradient in frame t, there's only two functions there, like ft and ft plus 1. right? And so that's true. And then at the endpoints, I just have one function involved, since x cap t appears only once and x0 appears only once in the top one, once in the bottom. Okay, so that's an easy thing. It's just a direct result of the way we've set up the problem, but we'll see in a little bit why it's super useful. Very related to that, something we've seen already, is the Hessian is the block tridiagonal, right? So we saw in the least square setting, so in the the least square setting, the Hessian is constant over all x, and solving that system of equations is what we have to just to solve the optimization program, period. But here, like the second derivative, it has the exact same block tridiagonal structure that the least squares problem has, right? And so that's also going to pay a little bit of dividends, and why how we can connect back to this this least squares. Okay, so those are the two key pieces of structure. The gradient, each frame of the gradient only involves two functions, and almost exactly the same statement as the Hessian is tridiagonal. The second derivative has this block structure. Okay, good. So what can we say about solving this problem? So I'll say a little bit about what we can say and then how we say it. Because the argument is, if you make a strong assumption here at the beginning, the argument's easy. Then I'll talk about how we can relax the strong assumption. Okay, so again, here's the what we'll say we can do. And again, I'll relax this in a second. So if you don't like this, don't get too upset. So let's say, okay, so the way to think about this again is I have in my hand, I've seen T of these FTs, and I have the solution there, right? And so I have all these different estimates in each of these different frames from 0 to cap T. And now I'm going to add, or I'm going to increase this capital T. And I want to see how these solutions change. Okay, so now what I'm saying here is like, okay, if I can take a previous, so if I can take it once I add, say, a function cap ft, so for any of these, functions that I add, if I can initialize it at the old solution and then find a new initialization variable for the new the new set of optimization variables that I'm solving for. If I can find something like that that makes the norm of the gradient less than a constant, I can uniformly bound that overall T, then actually showing that there's a limit point for this, that as cap T progresses, as I'm adding more and more functions, my variables in this frame converge. I can show that that's true. And I can also show that the convergence is very fast, right? So again, it's some number less than one, basically to the difference of what frame you're looking at and how many frames in the future you want. So again, you get this super fast geometric convergence if these are true. So let's just talk about like why this happens. And this is again, this result is completely independent of any algorithm that you use to solve it. It is strictly just a property of this collection of functions and this optimization program itself, right? But actually, you can establish a result like this by looking at a particular algorithm for solving it and tracing through the steps to see how much time you update each of the different variables when I initialize to this old solution. And so the easiest algorithm you can have is gradient descent. So again, I'll stress that we're going to trace the steps to gradient descent here, but the end result is just a property of the solutions themselves. Okay, so what do we know? So we know here that each of these FT are smooth and strongly convex. That basically means they can be upper and lower bounded by quadratic functions. We know that, and so we know that their sum is also going to be smooth and strongly convex. And in fact, just going back to this slide, if each of the FT have smoothness parameter L, that means its gradient is Lipschitz with constant L. And that strong convexity parameter mu, this L, you can think of this as being the max of all the Lipschitz constants, and this mu as being the min of all the strong convexity constants. Okay, sorry. So so we know that the sum of functions is also strongly convex. And we know that strongly convex functions, gradient descent with a fixed but reasonable step size, we know that it converges linearly. It's just a fundamental result in optimization. Okay, that's good. So how we connect kind of the linear convergence of gradient descent with the convergence inside these frames is, okay, if we initialize our first answer at the old solution, that means when I look at the gradient of this new functional at this point, and it doesn't matter what I initialize the last thing to for this discussion, so I just wrote something here. The gradient's going to be equal to 0 everywhere except in the last 2 entries, the things that depend on the new optimization variables that I introduced. Okay, so that's interesting, and that again just comes from the fact that the gradient has the structure where it just involves a sum of these 2 functions. So what does that mean? It means, okay, if I have my old solution and then I take a single gradient descent step, right? All I'm doing is updating these last 2 variables. Right, and so what does that mean? It means that iteration 1, only the last 3 variables of the gradient are going to be non-zero. And then after the 3rd step, only the last 4 variables are going to be non-zero, et cetera. Okay, and so then the key thing is like, you know, as these gradient steps are being taken, I know I'm making linear progress in solving my problem. And then I also, because I have this kind of structure in the gradient, know that frame t isn't touched until iteration t minus cap t minus little t. Right, so if I just combine the known linear convergence of gradient descent along with this realization about the structure of the gradient in this problem, you get this result almost immediately. Okay, so that's, I mean, you know, it takes a little bit of effort to write down the argument carefully, but that's essentially the essence of it. Okay, so there's one complaint here, and I don't blame you if you have it, and that's that this condition is somehow unsatisfying. And the reason it's unsatisfying is, you know, I'm trying to, you know, I'm trying to describe properties of this sequence of solutions that I have. And in doing that, I'm making assumptions about the properties of the solutions because that I can't really verify. I don't really know beforehand. Right? This isn't just a property of the function ft. It's a property of the function ft and every function that came before it, because this is, you know, this is the solution to the minimization problem for all the functions that came before it. So it's not really, so it's not logically inconsistent. It's just not clear what it's telling me yet in terms of like basic properties of the functions that I've been given. Okay. But you can, and the argument's much more complicated, so I didn't really include too much of it here, but just as a preview here. So if you can say, you know, this Hessian is diagonally dominant, just as in the least squares case, and if I look at these, you know, problems in isolation, so if I just look at the minimizers of the functions, if I just consider them one at a time, if those are all bounded, so they all live within some radius of the origin, right? Then I can find a constant that upper bounds this gradient. This is a subtle point and one that's not easy to prove, but it happens to be true. Okay, and you really do need something like this because it's easy to come up with situations or examples of FT where everything diverges. It's like that's true even in the least squares case. It's easy to come up with the progressions of examples where things don't converge at all. Okay. You know, if these kind of mild conditions are true, so the Hessian is diagonally dominant, which you know, this mild condition just on the properties of the functions themselves, or their local minimizers are all localized in something, then I can use the bound here and the diagonal dominance parameters to find what this constant is. Okay. So just as a quick example, so just related to like the streaming reconstruction we had for least squares. Here's a nonlinear problem, one which ends up with something that's convex, that has the same streaming aspect to it, but isn't a least squares problem at all. And it's a Poisson process estimation problem. So here in the green dotted line here is a Poisson intensity process. And then what I have in the red down below here are arrival times. Right, and so when the intensity is higher, I tend to get more arrival times, and intensity is lower, I tend to get fewer arrival times. Right, so but you know what I observe are the timings of these red dots, and what I want to estimate is what this curve is, what the intensity is at any point in time. Okay, so there's a standard maximum likelihood approach for doing that. So I can find them, you know, put this in the maximum likelihood framework and sort of minimize over all functions lambda of t, and this is what the negative log likelihood function looks like, the thing that I want to minimize. I can again discretize, you know, what I'm doing here with a basis. So all this is doing is replacing lambda of t with a sum of these x's times some preset basis functions. And then, all I realize here is I have like a linear function of the xn here, and this a log of linear functions here. And so this is like what my optimization program looks like, right? So it's almost like an interior point relaxation for a linear program. Okay, but the point is this is a very nice convex problem, but it's not at all a least squares problem. Okay, and again, I can divide up these red dots into different frames and use different batches and break apart my intensity function into different frames, and I can set this up as a streaming optimization problem just as before. So here's my function of xt and xt minus 1. It's not a least squares problem anymore, but it's convex and nicely posed. Okay. So I do this and I say, okay, as I present the samples a little bit at a time. So here I have a couple batch of samples. I add a new batch in this middle frame. I get a new estimate. Add another batch in the next frame. Get a new estimate. This black dotted line, that's the estimate that I will get from all the samples. And then I can send then the colored lots are my local estimates, what I have based on my data so far. And you can see that it converges very quickly. So just again, 1 or 2 frames in the feature, things settle down very quickly. So again, it makes a lot of intuitive sense, but that's what kind of the theoretical results on the previous slide are trying to explain. Okay, one thing you can do, you can say, since I have this property where my solution settles down really quickly, what if I only update B frames in the past? Right. And so what you could say is if I do that, I'll converge to a different point. But the difference between that point and what would be if I didn't do any buffering at all, again, that will be small, exponentially small in the size of the buffer. This is a thing that's easy in the least squares case. In the convex case, it's not trivial just because you have some kind of accumulation of errors that you have to account for. But if you sort of keep track of everything through the analysis, you can show that this is true. So this is nice because again, it tells me basically if I have this, linear convergence property again, which I get tie back to original properties of these functions, I can get this buffer solution. Okay. One last thing is this tridiagonal structure, just algorithmically. We know a general approach for solving convex optimization problems is a Newton method. Newton method is standard, maybe computationally hard because it involves solving a system of equations at every step that involve the Hessian. But we know the Hessian is tridiagonal in this case. So we actually have a really good way to solve this each step in the Newton method just by using a forward-backward sweep, just as in the least squares case. So we have 2 nice computational results. I can use a finite buffer, and the Newton algorithm is super efficient. Again, that's not a terribly difficult realization once you know how to solve tridiagonal systems and that you can realize this Hessian is tridiagonal. So each Newton step looks like one of these forward-backward least square solves, and Newton algorithm tends to converge in very few iterations. So we can do this in very, very, very few sweeps will be necessary. Okay. And this is just a picture. This is just a similar picture to the table I had before, and saying like, okay, look, if I make the buffer 5 frames deep, I get like something like e to the minus 10 in accuracy. So this is demonstrating the theoretical result. Okay, so in my last 10 minutes here, let me talk about what we started talking about here. This idea of optimization on graphs. So we spent the first 40 minutes here just talking about optimization on these chain graphs. We're ultimately interested in, or now interested in, is again optimization problems on these dynamic graph topologies. So I have again optimization on the graph. The graph specifies how the functions at the different nodes share variables, and I want to know what happens when I add new nodes to this graph. In other words, I expect that I'll have to update solutions on on nodes that are close to the neighborhood of where I added this node. But I want reassurance that I don't have to update things that are too far away. Okay, and it turns out this is you can take the chain results you have and you can put them into this framework with just a couple things you need to worry about. So again, like where does this where did this type of problem that turn up again? So this is a little blurry. Sorry about that. Again, we looked at this localization problem. So there's this procedure in robotics called SLAM. So simultaneous localization and mapping. Basically, what it just means is a robot, as it's moving around, it's taking odometry, figuring out how far it's traveled by looking at its odometer, trying to figure out where its orientation was at each step. And it connects measurements together, both through this kind of odometry data, it's called, and by correlating landmarks that it sees at different parts, right? So you can abstract all of that away and say like, okay, what I have is I have an optimization problem where I'm trying to figure out a position and orientation at every step. And what I have between each of these steps is I have kind of a relative measurement, like what's the distance in between X2 and X3, and what's the difference in orientation between X2 and X3. Right, and then I can sort of connect things, not just necessarily in a line over time, but also as I see shared landmarks, I can also turn those into relative measurements of my position and orientation between two things. So there's a whole, again, field of study that in robotics where people worry about stuff like this. But it's nice because you can naturally pose this as a non-convex least squares problem. But you can also, there's also a nice semi-definite relaxation that was realized about 6 years ago that makes this you can think of this now as a convex problem on a dynamic graph. And here you'll be very interested in knowing, okay, when do I really know where I was at time X1? Okay, so, boiling this all down, when I add the red node here, do I really have to update all the other nodes? So again, here's like just, something which indicates you might not have to. So here I add the green node and I show how quickly all these other nodes update. So this is kind of a synthetic but complicated example. So we're just kind of just doing numerics first here. So I see as I add this green node, the solutions in the neighborhood change, but the solutions a couple hops away change almost not at all. All right, I add the green node, stuff near me, the solution changes, things far away happen numerical. So this is some numerical evidence indicating that maybe I don't. Here's something on real data where I have, again, I'm sort of mapping out this floor. I get some observations right here. How do I update the rest of the trajectory? Okay, stuff connected to me updates a little bit, but things far away, of course, don't have to be updated at all. Okay, so to understand this, right, so this is very much in the spirit of what we were talking about in the streaming optimization. The key thing here is I can collapse the graph into a path in between two nodes. So if I want to know, say, what happens at node 1, when I add node 8, right, what I do is I say, okay, let me just collapse F5 and F7 together, and then collapse F3 and F6 together, and F2 and F4 together. So everything that's kind of equidistant away, right? And then what I can do then is I have a chain, right? This chain doesn't have the original functions in it, it has sums of functions in it. And then I can basically apply my convergence result from the chain, where this exponent now is the graph distance between the node that I added and the node that I'm analyzing. Okay, that makes some amount of sense. What you need to worry about is when if I have not a toy graph, but a big graph, there could be a lot of functions added together. So when I add a bunch of these functions together, does that really affect my my structural properties, right? Because this L and these mu, these are Lipschitz gradient parameters and strong convexity parameters for the things that are inside these bubbles. So what's nice is, and it's actually, once you figure out what you need to know, it's not that hard a result to say like, okay, what I can do is I can bound, this L and this mu by, if I look at the kind of the Lipschitz gradient parameters Li, I could bound that L by the maximum of these Li times the chromatic number of this graph. So the coloring number for the graph itself. This is kind of easy. You have to basically need to, once you write stuff all down, it just comes in writing the sum of that and the sort of disjoint parts, which are the colors. And in general, like chromatic number, you can also sort of easily bound by like the degree, the maximum degree of the graph, or maximum degree plus 1 or something like that. So like, again, if the graph is reasonable degree, this tells you that this constant will be reasonably behaved. Okay, so now, like, not only structural properties of the functions that you have, but also structural properties of the graph itself are interesting to you. Okay, good. I'll kind of close here since I'm running out of time. Just by mentioning another general application area you might be interested in, and that's in this area of like multitask learning. And all multitask learning is I have a bunch of tasks I want to solve or tasks I want to learn. Each of those tasks can be specified by an different optimization program with a different set of optimization variables xi, but the tasks are related, and I encourage the tasks to be related by regularizing with some weighted distance in between these decision variables xi. So just by itself, these are a bunch of decoupled optimization programs. I could solve them each independently. But once I add this regularization on the graph, that makes everything coupled together. Okay, so I guess if you take like this penalty to be some kind of least squares thing, it's what's called graph diffusion. If I take just the standard L2, what's called the network lasso, I get things that tend to cluster together. It's like doing total variation minimization on the graph itself. And there are lots of other examples too. So all we're pointing out here is like, okay, I can think of, I've solved a multitask learning problem, and then I add a new task or a new set of tasks that has a small number of connections to the old task. And so how can I quickly update what my solutions are everywhere? And the results on the previous slide give you a framework for doing that. So there's this nice paper by Halleck et al. That kind of ties this to they have this nice example in their paper of like property prices in the Sacramento area, where there's features associated with each of these houses for sale, along with their physical locations. You can sort of embed it in this graph in two space. And then, what we can just do, just to illustrate this, again, on another real data set, is we have a solution, and then we add a cluster of houses down here. And then we can ask, how much does a solution change when the cluster on bottom is added? And again, we make another one of these heat maps. We see like, okay, in this sort of immediate area, maybe it changes by, 0.01 relative error. When I get far away here, it's only changing by thousands. And then up here, it's only changing in 1 part in a billion. So again, as I get farther away on the point of the graph, the solution to these problems is only changing by a little bit. Okay, so with that, I'll end. Happy to take any questions. We have, these two references are available online. We're currently writing up the solution to the graph problem. So thank you for your attention, and I'll happily take questions.